Hey kiddos, welcome back. We're continuing our discussion of acids and bases. Last time, if you remember, we talked about what a strong acid was, and we identified 6 strong acids. Do you remember what those 6 strong acids are? Let's take a quick quiz, okay? Let's go ahead and list them at the top of this page. 1, 2, 3, 4, 5. So without looking back on the previous page, see how many of the strong acids you can identify by formula. Go ahead and pause the video, see what you end up with. See you in a sec. All right, welcome back. How did you do? Let's see. Is HCl listed as one of your strong acids? Hydrochloric. How about HBr? Hydrobromic. HI? Hydroiodic acid. How about HNO3? Did you get that one? How about HClO4, perchloric acid? And then finally, H2SO4, sulfuric acid. Kiddos, you need to learn those 6 strong acids because remember, if you know the 6 strong acids, all the other acids are going to be considered weak. Now, do you remember the difference? Like, why are these considered strong acids? So do you remember the difference between strong acids and weak acids? Yeah, strong acids dissociate 100% of the time. Weak acids don't dissociate 100% of the time. So let's take a classic example. One of our favorites, acetic acid. When I add that to water, the proton is accepted by the water molecule. And it turns into the H3O plus ion, the hydronium ion, and we're left with the acetate ion. Now notice the arrow goes both ways here. That means it reaches an equilibrium. It does not go to completion. In fact, in some future videos, we're going to do some icebox problems with weak acids, and we're going to do some quantitative analysis related to pH of weak acids compared to pH of strong acids. So at any rate, in the forward reaction, you noticed that acetic acid, HC2H3O2, donated a proton, so it's an acid, and the water, H2O, accepted that proton, so it's my base. Now if I go backwards, the hydronium ion, H3O plus, donated the proton to the acetate ion. So the hydronium ion was the acid in the backwards reaction, and the acetate ion was the base. Now, if we cheat a little bit and remove water from this side of the reaction and the other side, we're left with this. And that's normally how we would write that, dissociation of acetic acid and water. Once again, notice the arrow goes both ways, meaning that it reaches an equilibrium. That means these guys dissociate into H pluses and acetate ions at the same rate that the H pluses are bonding with the acetate ions to form the molecule HC2H3O2 again. So it does not go to completion, it reaches an equilibrium. Now, the same type of thinking can be applied to bases, except for bases, we're going to be producing hydroxides instead of hydronium ions or protons in water. So if we were looking at the conductivity of bases in water, some of them would produce lots of hydroxides, and they would be much better electrolytes than those that when we place them in water, they were poor conductors. That means they don't produce lots of hydroxides. So there are some strong bases. The classic example is sodium hydroxide. When I place that in water, notice the arrow goes one way. This goes to completion. We form lots of sodium ions and hydroxide ions. Now let me give you a few equations for the dissociations of strong bases. We just showed you sodium hydroxide dissolving in water to form sodium and hydroxide ions. Potassium hydroxide can do the same thing. Rubidium hydroxide can do the same thing. Cesium hydroxide, calcium hydroxide, and barium hydroxide. These are some of our strong bases. There are actually a couple others I want to add to that list. So let's list the strong bases in this box over here. And just like the strong acids, kiddos, you're going to be responsible to learn those. So it turns out that the group 1 hydroxides are considered to be strong acids. So that would be lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, and cesium hydroxide. And it turns out that some of the group 2 hydroxides are also considered to be strong bases, and that would be calcium hydroxide and strontium hydroxide and barium hydroxide, just to put them in order for you. So those strong bases must be learned. Remember, they ionize 100% in water solutions. All other bases, then, are considered to be weak. So let's take a look at a weak base. Let's do methylamine, CH3NH2. Now, actually, in this graphic, there are a couple of things that bother me. There are some things that are wrong, and we're going to explore those things that are wrong with this graphic. First of all, let me draw the Lewis structure for methylamine for you. We have NH2, and then we have this methyl group, which is CH3, also attached to that nitrogen, and there's a lone pair of electrons on the nitrogen there. Since this can accept a proton, it's considered to be a base. Okay? So, let's take a look at this graphic and let's find out what's wrong with it. In fact, why don't you inspect it for a minute and take a look and see if you can find anything wrong with the graphic. Okay, yeah. Maybe you notice this. Since this is a weak base, didn't we say it reaches an equilibrium? So the arrow goes in both directions. Okay, that's one fix-it. Here's the other one that really stands out to me, and it's really quite annoying. It looks to me like methylamine ends up gaining a proton, doesn't it? So let's see. H2O donates a proton, right? And methylamine gains it. Well, I thought something that can accept a proton is not called an acid, it's called a base. Did you notice that? And H2O ended up becoming OH minus. It donated a proton. I thought things that donate a proton are called acids. So those two things are wrong with that graphic. Now on the other side, I'm pretty comfortable with this. The CH3NH3 plus ion ends up donating one of the protons to water. So that does lose a proton, so that is my conjugate acid. And the hydroxide gains that proton, so that is the conjugate base. At any rate, that graphic had a couple of things wrong with it, and I think it's interesting to look at it, and hopefully you found a couple of those things that were wrong. So weak bases, when they react with water, will not produce as many hydroxide ions. That's why they're considered to be weak bases. All right, now we're going to begin a discussion on water equilibrium, and we'll get to pH and pOH actually in the next video. But for this video, I want to end with talking about water equilibrium. You might remember a long time ago when we were talking about electrolytes and I did a demonstration for you, distilled water conducted electricity a very little bit. I can't remember what number blinky light came on, but it had a very, very small conductivity. Therefore, there must be some ions in pure water. Well, where do those ions come from? If all we have are H2O molecules in our distilled water, where do we get ions? Well, it turns out that water can react with water to form an acid and a base. So every once in a while, this water molecule, H2O, can donate a proton to another water molecule and turn it into H3O+. Now if this guy donates that proton, it becomes OH minus. Now how do I know that doesn't happen very often before it reaches an equilibrium? Yeah, I know it doesn't happen very often because the conductivity of a pure water solution is so very, very, very tiny. So the reaction here is H2O liquid reacts with H2O liquid to form, and I'm going to draw the arrows going both ways, kiddos, hydronium ions and hydroxide ions. Let's cheat just a little bit to make this look a little bit prettier. Let's go ahead and cross off water from this side, and let's get rid of water out of the hydronium ion. So when I do that, don't I have H pluses left over? So I could rewrite this equation as H2O liquid becoming H pluses and OH minuses. And if we want to write the equilibrium expression for this reaction, we're going to put products over reactants. And we're going to call the equilibrium constant for this reaction Kw, because this is the equilibrium constant for water, for pure water. So Kw would equal H plus, sometimes it's written as H3O pluses, times OH minus. Why don't I show H2O in this expression? That's right, because it's a liquid, and liquids and solids are left out of equilibrium expressions. So let's erase some of this. This equation here, you are going to need to learn. In pure water, it turns out, and this should make sense, that for every H plus or proton I make, I also make a hydroxide. Look at this equation. In pure water, for every one of these, don't I make one of those? Yes. And so the concentration of hydronium ions in pure water is 1.0 times 10 to the negative 7th molar. And that also turns out to be the equilibrium concentration of hydroxides in pure water. So if I wanted to solve for Kw, and I know these two concentrations, I should be able to do it. Kw equals 1.0 times 10 to the negative 7th times the hydroxide concentration, which is also 1.0 times 10 to the negative 7th, which will equal 1.0 times 10 to the negative 14th. Nope, that should say to the negative 14th. And that is the equilibrium constant for any water solution. This number here won't change. That's why we call it, after all, a constant. So the ion product of water is this expression right here, Kw, which we now know the numerical value for, 1.0 times 10 to the negative 14, is equal to the proton concentration, hydronium ion concentration, times the hydroxide concentration. So in any water solution, this is a profundity here, H plus times OH minus will always equal 1.0 times 10 to the negative 14th. Now I've written this with two significant figures, but in reality it's a definition. It has infinite sig figs. So let's write that down there, infinite sig figs for that Kw value. All right, now we're going to apply that in our next video. For this video, I just wanted to introduce it to you. Okay, see you soon. Bye-bye.